Have you ever watched footage of a rocket landing vertically on its own engines and felt that what you were seeing seemed to defy some fundamental law of physics? You are not wrong to feel that way. For decades, the brightest aerospace engineers in the world considered landing a rocket in a controlled manner on solid ground to be a problem so difficult that it was not even worth attempting seriously, and that the practical solution was simply to let the used stages fall into the ocean and build new ones for each launch. When SpaceX announced it would attempt to recover and reuse the first stage of the Falcon 9 through a vertical propulsive landing, the reaction from much of the aerospace community was one of deep skepticism. Not because the idea was new, but because the technical challenges of executing it reliably and repeatably seemed almost insurmountable. And when on December 21st, 2015, the Falcon 9 first stage landed vertically at Kennedy Space Center, becoming the first orbital rocket to successfully land after completing its mission, it was not simply a technological milestone. It was the demonstration that a problem the aerospace industry had considered too difficult for more than half a century could be solved with the right combination of control engineering, modern computing, and an institutional willingness to accept the risk of failure during the development process. To understand why landing a rocket is so extraordinarily difficult, you have to start by understanding what condition the first stage is in at the moment its engines shut down and it separates from the second stage. At that instant, the stage is at an altitude of between 60 and 80 kilometers, traveling at speeds of between 2,000 and 2,500 meters per second, approximately 6 or 7 times the speed of sound, in a direction that is largely horizontal because the rocket has been executing the gravity turn during ascent. The stage has to get from that initial state to a landing pad on solid ground or on a drone ship in the ocean, stopping exactly over the landing point with zero velocity relative to the ground in a vertical position, without having been destroyed during re-entry into the atmosphere and with enough propellant remaining to execute the control burns throughout the entire process. And all of this has to happen in approximately 8 minutes from separation to landing, with a position error in the final touchdown that in the best Falcon 9 landings is less than 1 meter from the center of the target pad. The first problem the stage has to solve after separation is re-entry into the atmosphere. A rocket stage returning to Earth has to face the same physics that confront the re-entry vehicles of space capsules or shuttles. The compression of air in front of the vehicle at hypersonic speeds generates temperatures that can destroy the metal structure in seconds if not correctly managed. But unlike a space capsule, which is specifically designed for re-entry with a heat shield at its base and an aerodynamic geometry that orients it stably during descent, a rocket stage is essentially a long, thin cylinder with engines at one end, and its re-entry has to occur with the engines pointing downward, which is the orientation it needs for landing. This geometry is aerodynamically unstable during re-entry. The aerodynamic center of pressure of the cylinder is ahead of its center of mass when it descends with the engines facing down, which causes the vehicle to tend to flip and orient itself nose down, which is the aerodynamically stable position, but places the engines at the top where they cannot be used for landing. To prevent this flip and maintain the correct orientation during re-entry, the Falcon 9 uses a combination of grid fins and engine burns. Grid fins are aerodynamic control surfaces formed by metal honeycomb structures that deploy near the top of the stage and can be oriented at different angles to generate aerodynamic forces that control the vehicle's orientation during the phase of the trajectory where air density is sufficient for aerodynamic forces to be effective. Before the vehicle reaches the dense part of the atmosphere where the grid fins can function, attitude control is exercised by coal gas thrusters, small nitrogen gas propulsors that generate control forces in vacuum or near vacuum. The re-entry burn, performed at altitudes of between 40 and 70 kilometers, uses 3 of the stage's 9 Merlin engines to reduce the descent velocity before entering the denser atmospheric region, reducing the thermal and aerodynamic load on the structure during the most intense phase of re-entry. The thermal load during re-entry is one of the most severe challenges the stage has to overcome. Although the Falcon 9's re-entry velocity of 2,000 to 2,500 meters per second is significantly lower than the re-entry velocity of a capsule returning from orbit, which can be 7 or 8 kilometers per second, the aerodynamic heating it generates is sufficient to damage unprotected components. The Merlin engines, which are at the bottom of the stage and are the most critical structure that has to survive intact for landing, are protected by a combination of their own thermal mass, the cooling effect of residual propellant in the fuel lines, and an octagonal heat shield called the octaweb that surrounds the base of the engines and is made of heat-resistant materials. The grid fins, which are made of titanium precisely because this material has high temperature resistance and good structural strength with relatively low density, can reach temperatures of several hundred degrees Celsius during re-entry and continue functioning correctly thanks to their mechanical properties at high temperature. The guidance problem during atmospheric descent is where the control complexity of the system becomes most apparent. A rocket stage descending vertically with engines pointing downward has no conventional aerodynamics to stabilize it. Unlike an airplane, which generates lift and can be controlled by deflecting aerodynamic control surfaces with relatively little energy expenditure, a rocket descending vertically has to use its own engines to control its position and velocity, which implies a continuous expenditure of propellant. The guidance algorithm that determines when to ignite the engines, how many engines to ignite, at what thrust level to operate, and in what direction to vector the thrust to simultaneously control the position, velocity, and orientation of the vehicle is one of the most complex optimal control problems solved in real time in any engineering system currently in operation. The Falcon 9 landing algorithm is an implementation of what in the optimal control literature is called powered descent guidance, a type of control problem where the objective is to bring the vehicle from its current state of position and velocity to the target state of zero position and zero velocity relative to the landing point, minimizing propellant consumption subject to the physical constraints of the system, which include the thrust limits of the engines, the structural acceleration limits of the vehicle, and the orientation constraints imposed by the geometry of the propulsion system. This type of problem was studied mathematically in the context of NASA's Apollo program during the 1960s, when engineers needed to calculate optimal descent trajectories for the lunar module, and the mathematical solutions developed then form the theoretical basis of the algorithms SpaceX implemented in the Falcon 9. The difference is that in the case of the lunar module, the algorithm calculated a trajectory that was then executed by the pilot or the autopilot system with human intervention. In the case of the Falcon 9, the algorithm has to calculate and execute the trajectory completely autonomously without any human intervention. In real time during the descent, the computing speed needed to execute this algorithm in real time is one of the factors that makes autonomous rocket landing only possible with modern computing. The algorithm has to recalculate the optimal descent trajectory several times per second because any deviation from the vehicle's predicted state caused by a wind gust, a variation in engine thrust, or a sensor measurement error requires a complete recalculation of the optimal trajectory from the current state. In the early days of the Apollo program, this calculation took seconds on the most powerful computers available, making it impractical for real-time control of a vehicle descending at hundreds of meters per second. Modern processors can execute the same calculation thousands of times per second, allowing truly real-time control that can adapt to environmental disturbances almost instantaneously. The sensors that provide the guidance algorithm with information about the vehicle's current state are another critical component of the landing system. The inertial measurement unit provides real-time measurements of acceleration and angular velocity. But as we have seen in other contexts, integrating these measurements accumulates errors over time. To correct these errors and provide a precise estimate of the vehicle's position relative to the landing pad, the Falcon 9 uses a combination of GPS, which provides absolute position with meter precision, but can have latencies that make it insufficient on its own for precise control in the final landing phase, and a radar navigation system that measures distance and velocity relative to the ground with great precision in the last moments before landing. Fusing all of this sensor data into an estimate of the vehicle's state that is precise enough to guide the landing is itself a signal processing problem of considerable complexity. The final landing burn, which is the engine burn that decelerates the vehicle from its descent velocity to zero velocity exactly at the moment it reaches the ground, is the most critical and most spectacular event in the entire process. This burn is initiated at an altitude of approximately 2 kilometers, when the vehicle is descending at speeds of several hundred meters per second, and has to bring it to zero velocity exactly at the moment of ground contact. The timing of this burn is of extraordinary precision. If the burn is initiated too early, the vehicle runs out of velocity at too high an altitude and falls freely from there, which probably results in its destruction. If it is initiated too late, the vehicle impacts the ground with excessive residual velocity, also resulting in its destruction. The time window within which to initiate the burn and produce a correct landing is fractions of a second, and precisely determining that moment requires knowing the vehicle's altitude, its vertical velocity, and the engine's thrust curve with a precision that only modern sensors and sophisticated state estimation algorithms can provide. Wind is one of the environmental factors that most complicates landing on solid ground compared to landing on a drone ship in the ocean. Landing pads on land can be located in places where wind patterns are reasonably predictable, and where landing windows can be chosen to avoid excessive wind conditions. But in any case, crosswind during the landing burn generates forces on the vehicle that the control system has to compensate by vectoring the engine thrust to generate a horizontal component that counteracts the wind-induced drift. The speed and direction of wind at different points on the descent trajectory are measured by meteorological sensors and communicated to the vehicle's control system, which incorporates them into its calculation of the optimal trajectory. But wind is inherently turbulent and variable, and wind gusts that are not predicted by meteorological models represent a source of perturbation that the control system has to handle reactively. The landing legs are another system component that seems simple but conceals significant engineering. The 4 legs of the Falcon 9 are folded against the body of the stage during ascent to reduce aerodynamic drag, and they deploy seconds before landing via pyrotechnic actuators that extend them to their landing position in less than a second. The legs have to be strong enough to absorb the landing impact, which, although the control system minimizes vertical velocity, still implies significant impact forces on the legs and the stage structure. At the same time, the legs have to be light enough not to excessively compromise the mass fraction of the stage, because every kilogram the landing leg system weighs is a kilogram that cannot be payload on launch. The design of the Falcon 9's legs, which use a combination of high-strength aluminum and carbon fiber, represents the compromise between structural strength, impact absorption capacity, and minimum weight that is characteristic of all rocket design. What the complete story of rocket landing reveals, when examined in depth, is that this achievement is not the result of a single brilliant technological innovation. It is the result of the convergence of multiple advances in computing, optimal control algorithms, precision sensors, high-strength, low-density materials, and propulsion systems with precise throttling capability, all maturing simultaneously at the moment SpaceX decided to attempt it. Each of these components separately had existed in less mature forms for decades. What SpaceX did was recognize that the simultaneous maturity of all of them had created a technological window of opportunity, and had the willingness to invest the resources and accept the initial failures necessary to integrate them into a functional system. The first Falcon 9 landing attempts failed in ways that sometimes resulted in spectacular explosions on the landing pad. But each failure produced data that informed the necessary corrections in the control algorithms and mechanical systems, until the system reached the level of reliability that makes successful landings seem routine today. The next time you see footage of a rocket landing vertically on its own engines, with the column of fire pointing downward and the vehicle decelerating to zero velocity exactly at the moment of ground contact, remember that what you are seeing is not a demonstration of brute force. It is the real-time resolution of one of the most complex optimal control problems engineering has ever tackled, executed by algorithms running on processors that recalculate the optimal trajectory thousands of times per second, fed by sensors that measure the vehicle's position and velocity with centimeter precision, and executed by engines that can throttle their thrust with a fineness that would have been impossible with the technology of previous generations. And that, behind those few minutes of spectacular descent, lie decades of accumulated mathematics, physics, and engineering, waiting for the moment when technology was ready to make them a reality.